All right. Hey everyone. Here you guys are already planning spring break activities and things. You guys ready for the break?
Oh yeah.
It's kind of strange for me. This is the only class I'm teaching this semester, and like we just had a full week break from this class. So it's like, oh, get a break and then teach a week and then another break. So it's interesting. I'm happy to have it. Sad we're not going to Nicaragua, but here we are. Okay, so today I'm going to kind of pick up where we left off last time with the latrines and really talk about the composting component. So thinking about, okay, how do we deal with solids, really composting pit latrines of some sort, or I guess composting latrines of some sort. So I have a kind of a variety of things to show you today, some of which is like high-tech stuff, some of it's just the principles of kind of what it takes to compost biosolids into something that's safe and usable for using as fertilizer. And so that's kind of what we're going to do in terms of kind of today's lecture. So we talked about the basics of latrines last time. Today I'm going to start us with talking about this autarky thing. This is a fancy, I think, one of the Reinvent the Toilet outcomes from, I think that was a Bill and Melinda Gates, the Gates Foundation initiative some time ago, was to create a toilet that essentially could, you know, has enough innovations and everything to create fertilizer and to clean everything in-house. So this is a kind of a high-tech solution. There's lots of infrastructure involved, but it's also kind of standalone. And within this unit, essentially, and maybe I think it's all in that one box you see, it can process human waste essentially completely to the point where you can safely discharge the water, and you can reuse, you can essentially collect a fertilizer. So I'm going to show you a video on that. It's unfortunately not in English. This is, actually I visited and used that facility once. It's in Switzerland. I got a chance to visit it's a kind of a university research technology sort of a place called EVEG. You'll see in a moment. And in Switzerland, there's several different languages they speak. In the West, I think it's Swiss French, kind of a Swiss dialect of French. And you've got Swiss German, and I think that's what this person speaking. There's some captions, so it'll make some sense, but it, you know, kind of sounds interesting. And then I think there's also a third language. It's sort of historical Swiss or something. I don't remember what it's called, but it's interesting linguistically. And anyway, okay. So let me pull up that. There's first of all a brochure on the whole thing. I will post this in case you're curious. It kind of goes into some more of the depth. I'll take a look back through this in a moment, but I'll go ahead and play the video for you here. Pardon me a moment while I get the sound situation set up.
Hier sind wir jetzt im autarken WC drin. Was wir hier sehen, ist ein WC, das auf den ersten Blick völlig normal aussieht, in Wirklichkeit aber der Urin trennt. Der Urin wird unten dran separat gesammelt. Nebendran haben wir ein wasserloses Urinal, wo wir auch den Urin sammeln. Und als drittes Element haben wir ein Handwaschbecken mit recyceltem Grauwasser, wo man sich nach dem Toilettengang die Hand waschen kann. Nach der getrennten Sammlung vom Urin trennen wir hier noch das Spielwasser von den Feststoffen trennen. Das Wasser fließt rein, wird durch die Schleuderkraft wieder rausgedrückt und hinten im Abwassertank gesammelt, und Feststoffe fallen direkt in den grauen Fäkalientank. Gerade nebendran sieht man den ersten Schritt der Urinbehandlung, die sogenannte Stabilisierung. Oben sehen wir stabilisierte Urinskalen, unten das Weiße ist Calciumhydroxid, wo wir zum Stabilisieren beigeben. Der Tank wird regelmäßig durchmischt. Das Ziel von der Stabilisierung ist, dass man einerseits Krankheitserreger abtöten und andererseits verhindern, dass Nährstoffe verloren gehen. Das ist der zweite Teil von der Urinbehandlung. Da sehen wir den Verdunstungsreaktor. Da wird die heiße Luft angesaugt und verdunstet das Wasser im Urin. Der Urin fließt auf die Tafel an. So sieht es mit frischem Urin aus, bis er trocken ist. Dann kann man abkratzen. So. Und am Schluss haben wir ein Nährstoffkonzentrat, ein Trocknungs, das man in der Landwirtschaft als Dünger brauchen kann. Wir kommen hier zur Wasserbehandlung. Was wir hier haben, ist ein geschlossener Wasserkreislauf. Im ersten Teil wird das Wasser biologisch behandelt, fließt dann durch die Ultrafiltrationsmembrane und wird aufgepumpt, oben links in den Aktivkohlefilter. Nach dem Aktivkohlefilter geht es in den letzten Teil der Behandlung. Ihr seht dort oben eine Elektrolysezelle. Die produziert eigentlich laufend ein bisschen Chlor, wo das Wasser desinfiziert. So wissen wir, dass Wasser zum Handwaschen und zum Spülen sicher wiederverwendet werden.
Das ist der Vorlagetank, in dem die Fäkalien gelagert werden. Den mache ich mal zu, weil es ziemlich stinkt. Und dann werden die Fäkalien aus dem Tank mit der Zerhackerpumpe in einen Bereich geführt, wo sie zwischengelagert werden. Dann werden sie mit Luft beaufschlagt und dann wird das Ventil zum Reaktor geöffnet. Das heißt, die Luft schießt dann die Fäkalien in den heißen Reaktor und dann findet die Reaktion statt. Das ist eine Verbrennung. Die Temperatur, die da drin herrschen, sind zwischen 400 und 600 Grad Celsius und der Druck liegt ungefähr bei 300 Bar. Nach einer gewissen Zeit, wenn die Reaktion abgeschlossen ist, wird das Ventil am Ende vom Reaktor geöffnet und die Produkte werden in den Phasenseparator oder Kondensator entlassen. Und das Produkt, das dann rauskommt, in dem Fall, sieht so aus. Also wir haben hier die Flüssigkeit und die Asche, die sich schon am Boden abgesetzt hat.
All right. So, what do you think? Interesting? Would you use that fertilizer? Let me get the lights back on. Yeah, so there's a very interesting kind of setup there. I guess we'll kind of a neat design. Obviously not super conducive for low cost. You saw lots of fancy equipment there. It's kind of neat that you can make one unit like that and then kind of have nearly self-sufficient. I think there's energy inputs, especially with the incinerator. There have been similar designs to try to make something like that that's all solar powered and then perhaps do electrolysis only to treat the fecal matter and stuff. So this is just kind of one sort of thing that's out there as a technology. Pretty interesting. Essentially they're separating the gray water, which would be the hand washing. They're going to separate the urine as best they can, and then essentially modulize the different treatment steps. So you could have the urine processing, drying it out. It turns out urine is typically, or should be generally free of pathogens. Somebody has to have an active, like a kidney infection or something like that, in order for you to expect pathogens. So it's possible and worth some concern, but generally it's actually not very unsanitary. So the direct drying of it is probably going to kill any pathogens that might have been remaining, and generally you don't have bacteria able to propagate in a very hot, dry environment. So that's probably enough processing, just simply drying it that way for certain uses. Okay, so then this brochure, which I will post for you, you've got the link here, and I'll post the slides as well, obviously. I think I'm a little behind on the slides. I will, just kind of a side note, I'll get all of that stuff squared away in the next couple days. And I'm aiming to have your introduction paragraphs graded and back to you by Friday as well, so I can post to Moodle. Actually, I should probably, since I'm going to show you that, or give you that before spring break, I need to talk about that in a moment. So I'll come back to that. Anyway, so lots of neat things about this autarky thing. The goal here is a self-sustaining or can do everything all in the one little spot. Okay, and they envision several uses for it and all that. Okay, so let me comment on the grading. I've done a few of your introductions so far. I'm going to give you a grade that is kind of shows as if this was the whole paper in some sense, or like this was telling of the whole paper. So if you hadn't included references yet, it's going to look, the grade will look bad, but don't worry, because I've told you up front that I encourage you to go ahead and start adding the references, getting that practiced, but I'm not like requiring it. So this grade is not a permanent grade. So the intro, it's going to be replaced by your next draft. Just straight replace. It's not going to be like the average of the two. So I'm just going to take the next draft and replace it. So assuming you do better on the draft, you'll be able to see how your grade is going to climb from this point. And like I said, so you'll get a 0 for the references if you didn't use any or do any of that. But don't worry, because when you do, that'll be fine, and that's not going to impact you in any permanent manner. So that's my plan, and so what I'll do is just kind of give you that as a placeholder to let you know. So don't be scared if you see that. Most of what I'll report on Friday is participation. For the presentation itself, the primary form of feedback was your peer feedback. I'm giving you a grade, but that's actually just a participation grade for that day. Kind of my assessment, just a really quick, how prepared, how well did you present yourself in that moment. So that's going to be just one of your participation scores amongst many. And participation, of course, is a little bit, I have a little bit of subjective say by the end of the semester, so even that is not necessarily binding, and I basically everyone came and participated pretty much, so you scored pretty well in general, so don't worry too much about that. I just wanted to tell you what you're going to see when I give you the grade report and all that, and what you'll see in Moodle, and that should be in Moodle by Friday, because that's when I'm supposed to do that. Okay, any questions on that? Okay, so back to the autarky stuff here. So essentially they give a little definition saying economic independence or self-sufficiency. So that's sort of the idea there is they want to make units like this that would be economically self-sufficient. So producing the fertilizers actually could be a valuable commodity that could be sold, and so that's sort of the thing. Obviously, with the if you're thinking about it in a the example they give, a utopian dream, certainly there's some aspects of this that's not realistic and should not be pushed too far. Assuming that a very poor community would actually benefit from the technology that is bound to break is not such a good idea, right? Okay, so that kind of just a brief picture of one, I guess the high-tech route to providing some sort of biosolids reuse, treatment, recycle, all that. So generally, if we're thinking about it in terms of composting, kind of the simpler, low-tech method, there's a few things we ought to, we have to consider. Some of this is going to be a little bit obvious, but okay, pathogen reduction. If we're going to reuse the stuff at all, the whole point in having some sort of a waste handling system is to eliminate the transfer of pathogens and or confine it to a certain location that's going to be away from human contact. So during the process, you want to reduce the pathogens to some level which is going to be safe for your intended use. And you're going to, while you're doing that, you want to contain it, separate it away from human contact. So there's some obvious concerns then if we have people shoveling contaminated stuff in order to handle it and process it. So the less manual labor inputs we can have, or the more separate, more control, the better. Because again, if we're thinking about this realistically, we're going to have communities that are not going to have hand sanitizer and latex gloves to work with on a daily basis. Okay, the utility, again, relatively obvious, is fertilizer production. We talked about nitrogen, phosphorus, and didn't mention potassium, but that's another good one that we end up getting from biosolids and from urine composting or recycling. And then we're also getting a nice benefit from a reduction of solid waste. So we mentioned in the pit latrine situation, it's also true for septic systems. The solids buildup over time is a real cost that we expect to be incurred eventually. So disposal is a good thing. You can potentially harvest biogas. I'm not sure if that autarky system was doing that. I don't think so with their incinerator. Although maybe they mentioned it, maybe that's part of it and I just didn't notice. You'd have to do basically anaerobic incineration. So no oxygen, you're just driving off, you're just really high heat with no oxygen present. You might be able to get some biogas potentially, or through a biological process, anaerobic. I don't think that's what they were doing, but that's a potential you could do. Recover some energy from the waste in the form of methane, most likely. And finally, recovering some costs of whatever treatment you are doing, right? So that was kind of their goal with the autarky system, especially I think that urine-based fertilizer, bottle it to be sold for use in gardens or whatever. Okay, so what do we mean specifically when we're talking about biosolids composting? The technical term would be the aerobic thermophilic decomposition of organic constituents to a relatively stable humus-like material. So humus being like soil-type matter. If you grab a handful of potting soil, what do you call that? Soil, sort of. Humic substances is a term that we use to describe soil, organic material that is soil in nature or is soil-like. Okay, so that's a technical definition, and so what we can see there, that aerobic, that means we do have oxygen, so we have access to ventilation for the process. We have thermophilic, meaning liking heat, so a biological process that likes the heat and will do well with the heat. And then what it's doing is decomposing, so destroying or breaking apart the organic matter into simpler stuff, and ultimately forming this humus-like material. And that's going to, in some sense, homogenize it into something that looks a little bit like potting soil. Okay, so there's a few environmental factors to consider, and this is whether or not you're talking about kind of third world or industrial scale. In either case, you have to consider the moisture content. It's essential for the biology to go forward. You have to have enough moisture. But you also don't want to flood it with too much moisture, because that's going to ultimately lead to cases where you have anaerobic pockets, and that's going to kind of kill the process or disrupt the process and make it really awkward. So the control of the moisture content is really important. pH is going to be important. Temperature, oxygen concentration, all of those things are going to determine how long it's going to take and kind of the effectiveness at pathogen reduction. The microbial community kind of ties directly into that and is really reliant on several of those things. Essentially, it's a biological process. You want specific types of organisms to be growing. You expect different classes to be able to grow, and so you have to make sure that the conditions are proper for that to occur. Then you got to consider the material type. This also matters for what your yield, your outcome is going to be. If you're composting something that you've separated mostly urine, that's going to be a lot different than if you have urine mixed in. So, that, or if you're recycling food scraps into the compost and things like that, there's a lot of factors that are involved where you really may need some consideration for your endpoint based on what you're putting in. Okay, so then the biosolids, this is kind of an example here. I'm not positive. This image, you just find it if you search for biosolids. But I believe this is rows where they've essentially seeded in these biosolid kind of topsoil sort of deals. So that's what it would look like in practice. I think I have a couple more pictures. And ultimately what you want is something that's akin to topsoil or to potting soil that's going to be nutrient rich, arable, you mix it in with the soil, put it on top of the soil, and it should provide a lot of benefits. So if you, let's say, till it into soil, depending on the soil you had in the first place, there's a lot of benefits it can provide. So here's a bit of a list. So obviously, just the straight, the value coming from the fertilizer is also value coming from the fact that you might be able to take land that was not so arable, not so farmable, not so good for plants to grow, and then transition that into something that's going to be a much better foundation for crops to grow in. Okay, so offsetting some costs, providing the nutrients, including potassium, also some micronutrients if there's some things that plants need and aren't getting from the soil, or they're limited. All this organic matter is a good chance it's going to provide some of that as well. Some indications say it could reduce the need for pesticides. That may be the case if the plants are growing more healthy. They're not as susceptible to pathogenic, or I guess predatory action by insects, however you would say that. Insects attacking the plants, may have a little more better defense with better nutrient and given better soil. So increased water holding for soils, so the soil itself is functioning a little more ideally for the plants. If you had something that's not able to retain water, maybe it's a bunch of sand, too porous, well, this may help the soil retain more water. On the flip side, if you had something like clay, the addition and the mixing would probably give you better aeration and drainage through that type of soil. So it's kind of, again, that middle ground thing that's going to help many soil types. Okay, these will lead to greater root depth. All of these things benefiting intended uses for the soil. Okay, yeah, and potentially decreasing the surface crusting, which would kind of cause runoff instead of rainwater penetration. Okay, a couple of disadvantages, and here's some more industrial application views here. You can potentially literally take a truck and spray it. In this form, it's going to be slightly liquid still, enough to pressurize through a pipe. And so you could spray it like that. You could take a tractor of it and have some sort of a sprayer on the back of that. And there's actually several potential disadvantages especially for the workers or for the people living nearby if you have a kind of a large scale system. Would also apply to small local communities depending on how much interaction they have directly with the biosolids, right? So once it's processed, it's relatively safe, but you still have odor. Is not going to be too pleasant, especially if the process perhaps did not get quite enough oxygen or something. There's definitely some potential for it to be pretty stinky. Survival of some primary pathogens in the product. We can expect that can and probably will happen to an extent. A lot of the designs are aimed at reducing by some amount. So if we had a lot of pathogens, but we reduce it by 99%, that means there's still some surviving, right? So we may have accomplished our treatment goals, but still there's there's some around, and that's a concern. There's also a concern if you're spraying, as you can kind of see in both of these cases. You may be creating aerosols, and there's a lot of fungi in this that have been growing with the process, with the biosolids process. So you actually have a fair amount of allergens produced and potential for kind of respiratory stress for people exposed. So the people that are doing the land application, I have heard stories or maybe heard of reports of that being a big problem for workers engaging in that activity, especially if not protected properly. Okay, then you also have a potential with lack of consistency, especially on a small scale system. If you have just a month where you just add in a whole bunch of banana peels and you don't normally, that may change the consistency. Or if you've ever done any composting at home, you can tell that it's going to look a lot different if you have kind of a different inputs, different temperature. Maybe you have it on a porch or something, and in the summer it's going to be a lot different than in the winter, right? There's different aspects that could affect the quality, could cause some problems. Heavy metals really is more of a concern for larger scale systems where you have a whole bunch of inputs all concentrating into the solids. So that's not as big of a deal for, let's say, an individual home or small community doing that. Okay, so a little bit about the formal processing and our kind of in the state side, at least, what constitutes biosolids and effective, appropriate biosolids treatment. So we categorize them into two classes. We have Class A and Class B. So Class A are the most stringent standards. They allow for public contact. And really what that's meaning is, if you were land applying them, you could do so let's say in a park or something like that, where you have a garden. Something like that would be allowable. For the no public contact, I think you have to keep it away from public roads by a set distance, and it really has to be on pretty much an agricultural site and I think there may also be restrictions with what types of crops you can put it on because of expected public contact with the produce. Okay, but Class B is useful for many cases where the agriculture is going to be benefited, and you don't have to have quite as high of a treatment standard. The processing can be quicker, but it's only allowed in certain cases. So a couple of things here. The regulatory requirements for the two, essentially, and by the way, I have a book I use for other classes sometimes with this material that I got this particular material for. So if you're curious about this in particular, just let me know and I'll get you connected with that book. So Class A, essentially we have two different types of composting that we can do. It's called aerated static pile or an in-vessel thing. And essentially you have to achieve at least 55 degrees Celsius for at least 3 days. So you have to have a temperature, elevated temperature, and really this is mostly elevated by biological activity, by the way. So you have to set up your system in such a way where the bacteria are going to and other microorganisms are going to generate enough heat to achieve 55 Celsius. So you're giving them lots of oxygen. This is why we call it thermophilic, because these microbes have to like the heat. Because if you were to think about, let's say, E. coli, just as an example, it's often in our guts. So it's pretty happy growing at 37 degrees Celsius. Some processes you can grow up to 44 degrees Celsius perhaps, and then you're really going to limit other types of coliforms. So 44 is kind of a limit. When we do some microbial experiments in my lab, if we're ever, sometimes we'll do a specific thing where we're going to add viruses and bacteria together, and we have to make sure that when we're we end up working with kind of a heated substance that we're going to pour them into. And when we do that, we actually have to make sure the temperature is really not much higher than 44, because we're going to put the bacteria in there, and if it's too hot, they're just going to die immediately. So 50 degrees Celsius is enough to kill our E. coli pretty quick, as an example. So they're pretty happy there. They're kind of, they're okay. So we'll give a smiley face, awkward face, and a unhappy face here, right? For those temperatures for E. coli, just as an example. Okay, so that kind of gives you an idea of how this is going to impact most pathogens that could infect somebody's gut. Probably going to act similarly to E. coli there, whereas you can get some microorganisms that are okay there. So for class B then, there's a method, well, I think there's a variety of methods that can produce them, and we're going to go through a couple of them. But this windrow method, that requires 55 degrees Celsius for at least 15 days with 5 turns. Let's see. Let's see. Oh, I'm sorry. I think what happened here is it was not clear the separation. So I think that's class A above that line and class B below it. Okay, so then there's another strategy for class A windrow. We'll take a look at that in a minute. 55 degrees Celsius for at least 15 days with 5 turns. So essentially, this is occasional oxygenation. So only occasionally do you mix it. I don't know if we need 2 S's there, I'm going to assume. So occasional aeration versus constant. Because otherwise, I mean, it sounds like that's a lot higher, a lot longer of a time frame to have that high of a temperature. But I think the deal is, when you mix it at least 5 times, that's going to make sure that everything's aerated properly, and so you have enough mixing. Whereas the aerated static pile or the in-vessel, we'll see you have air flowing through it pretty much constantly to provide the aeration. Okay, so then class B then is 40 degrees Celsius or higher for 5 days, during which the temperature exceeded 55 degrees Celsius for at least 4 hours. So you can see then that you have to hit that 55 mark for at least 4 hours out of 5 days. You know, perhaps your temperature profile, you know, starts kind of low. You hit the 40 mark, and then eventually you kind of hit a spot, and then it tapers back down. And if this is the 55 mark, you know, that's going to require less energy input, less process, design, or whatever input, and a quicker time than if you had to do for the class A. You had to be up here already and stay up there for the 5 days, right? If this was like a 5-day period here. Okay, so that's kind of giving a bit of an example, and you see that requirement for 4 hours, that should kill most or at least many of the bacteria there. And of course, you're also not measuring the temperature in the whole thing. You probably just have a temperature probe or maybe a few put inside your compost to test it, you know, in a few locations. So it's you have to hit a reading, and there's probably some method for how you measure that, but there's potential for it to not be exact, especially in that class B. Okay, so a few things here about the metals. So maximum metal concentrations in biosolids. So there's a sealing and a pollutant concentration. I believe this sealing is the total, like above this, you're just simply not allowed to apply it, I think. I'd have to go back and read through it again. Or it may be the concentration in the land itself that we're targeting. I think there's regulations on both sides, like the eventual total accumulation for the land that you're applying it to, and then you'll reach a ceiling, and then you can no longer apply any more there. And then perhaps over here is just the Okay, so maybe this is regards to the land, and I'd have to go look this up. But I think right now this would be the land and this would be the biosolids. So then arsenic, and what we're dealing with here is milligrams per kilogram. So milligrams of arsenic per kilogram of soil or biosolids. So we see all these lists here. Copper is not a big problem, but it is a concern. So all of these, I guess they're basically derived based on how much we would expect to matter in terms of how much a plant would take up and then contain in the plant itself. Okay, so the process steps, how do we actually do composting? The first thing we need to do is dewater it, or really adjust the water amount as needed. And sometimes we'll also need to add a bulking agent to give it, so if it's too, let's say, mud-like, then we might add a bulking agent, which oftentimes is just sawdust or something like that, to allow the material to then be a little more of a mixture rather than a sludge, if that makes sense. Kind of a mixture with particles that's, you know, maybe a little more porous so air can go through, rather than a sludge-like clump of mud, water type stuff. Okay, so, and that's what this says: porosity, moisture control, so sawdust, rice hulls, coconut husks, stuff like that. So really just any sort of a byproduct of food or lumber processing could be used. It's something organic that can be decomposed. It's not really going to impact anything. We're not going to harm the bacteria or anybody with it, and you might as well dispose of it, so that's a pretty good way. Okay, not always needed, but can be helpful. Okay, so you get this mixture to a decent consistency, so that's the dewatering, the bulking. Then you achieve some temperature between 55 and 65. I think if you let it go too high, you have to be careful because A, you'll kill the bacteria or the microbes that you're intending to work with, and B, you can actually end up getting runaway reactions if you have the wrong conditions, especially if you had some anaerobic spots, and then you have exothermic reactions creating more exothermic reactions, and suddenly you have a giant pile of crap on fire. And that's not a pretty thing. So there's actually, and that's a concern as well for landfills actually. Landfill operation has to be done in such a way to prevent landfill fires, because it's a pretty dangerous and terrible thing. It's going to be lots of noxious gases. You're not going to have complete combustion of anything under the ground, and if it's a fire like that, it's actually a pretty serious problem. Okay, so you want to do that, and that will, if you keep it there, that's going to, again, do the pathogen control, and you're going to also be causing evaporation slowly during that process, so it will dewater the solids and have a little bit of drier solids by the end of it. Okay, you have to give it some time to stabilize after the composting step. That's going to be lower temperature, kind of letting things settle. That's I guess kind of the final step of the actual processing in some sense. Additional drying if needed, depends on how you're going to use it, ship it, all that. And sometimes, I guess you could then separate it back out from the bulking agents, maybe doing some sort of sieving or filtration of some sort. Okay, speaking of moisture content, we really have to hit the right moisture content, so it has to be good enough for bacteria to grow, but not too much, like I mentioned earlier, to prevent oxygen and all that. So the ideal is about 40 to 60%. So you have to have really 40% moisture content or better. So that's actually a lot of water, right? So this is going to be a mass basis. So 40% of the biosolid stuff is going to be constituted by water. If you have less than like 15%, you're just going to inhibit basically all bacterial activity. So that's a big no-go. Less than 40%, you're looking at a case where you may be inhibiting the bacteria. They just don't quite have enough moisture to work with. And I believe this is to start the process. So as some evaporation occurs, you expect that to be decreasing over time. And so really this inhibition is probably some areas of the soil getting too dried out from evaporation by the end of it to carry the biological process through the whole thing. Okay, so we have some optimal amount here, so 50 to 60% of it should be water. And then above 60%, you're just typically too muddy. So at that point, you'd want to dewater or maybe look into a lot of bulking agents. Okay, so here we have a figure that's showing essentially the sludge solids percent. So what percent of it is solids versus liquids. And this is for some given compost operation. This curve, you can get a curve like this that's going to depend on your particular composting activity. And so on the left, we have a mixing ratio in terms of how much bulking agent you might have to add. So this is a wood chip volume, for example, per sludge volume. So some mixing ratio of how much of your wood chips do you add for your sludge. And if the sludge solids here is 10%, that means 90% water. You have to add 5 times about, or 4 times the amount of wood chips as you have sludge, right? So then if you take a look, as you hit about 50%, what we were talking about, and really what we were talking about was anywhere between 40% water to 60% water, or 40% to 60% solids. So that's kind of the range where, if you have less than 50% of it as water, maybe you don't even need a bulking agent. Maybe you're good already. So then when you're thinking about your dewatering and all of that, that's something to consider. I haven't done any composting myself since I was a kid, and my mom had something on her back porch sometimes where we would add some worms, throw in our coffee grounds, banana peels, whatever. Certainly not a biosolids composting, but thinking about it now, I'm like, I wonder, would this process have been, how would I approach that process now? Should I add a bit of water to it before, as it's going, like put a thermometer in there? The scientist in me is now kind of thinking back on it. It's like, if I was to do this for, let's say, in my backyard or something, how would I do that differently now? Okay, so the approaches we mentioned earlier, and again, this is really kind of the industrial scale portion so that we can understand the needs if we're going to design something similar, like what are the needs, the process needs for it to happen. So that's why I'm going into kind of the industrial scale, even though it might not be as relevant directly to our class. So the first is a aerated static pile. Essentially, we have a bunch of our biosolids, sludge stuff. We can make a pile, and then we essentially add some sort of a cover or blanket type thing on top that's porous to the air, and then we pull air through that. So we're going to pull air through the pile into some pipes here. So presumably that sludge has to be porous enough to allow some airflow through it, and that's going to oxygenate the entire system. And having the airflow here, of course, we're also going to get a lot of water seepage during this process, so that has to be collected, and that's collected here. So then that'll be some drain to a wastewater treatment, probably back to the front of the wastewater treatment train. But with that, we can then extract air and exhaust it through some sort of a filter. Maybe that's just a pile of screen compost, maybe just finishing the compost there, or some other filter type. And just really, we're essentially moving air through the system. That's the static pile process. And what you can see here is it's not necessarily a continuous process, right? You have to assemble the pile, you have to blow air through it for at least 5 days of a certain temperature if you're going for the Class A solids, which this type of arrangement I think that's generally what you're targeting. So really you have to probably have that pile there for maybe a week or something, because it's going to take some time to ramp up, and then maybe you move it to do the stabilization, or maybe you just let it sit there for a couple more days with less airflow or something, or I would guess you'd move it somewhere and let it be out of the pile formation. But in any case, that's a fairly long process for just getting this one segment. It's sort of a batch process type of deal. So that's a bit in contrast with what we might say as an in-vessel system. We mentioned that's the other way to get a Class A biosolids. And so here you can design it any which way you want, but essentially you're going to have some type of a plug flow reactor where you have the ability to do sort of continuous. So you have solids being added to one end, and by the time they slowly get to the other end, presumably you'll be able to take that stuff out, and it will have experienced 5 days worth of the right conditions. So in one of these you'll have, let's say, compost being added to the top here. It's slowly flowing, so to speak, downwards. You're adding air in here, so air is being being injected through it there, and kind of flowing up through the pores upwards, and you'd just be then collecting your biosolids out here. And so that would be your residence time there, assuming you're keeping this at 55 Celsius or more. You could have a residence time of 5 days in that vessel, and that would be the way. Several different ways to design this. You could do kind of a graded system, maybe with some porous media air injection system, and some, this is essentially a mechanical screw here, I think, that's extracting the biosolids that way. You could have something that goes left to right, it's a kind of a horizontal instead of a vertical system. All sorts of ways you can design a composting reactor like that. A couple more examples. Some of these, it might make sense to sequence an anaerobic chamber where you can harvest biogas, so that'd be methane. And I've got a little video on that if we can get there. I think we'll get there. So that's another potential option for processing if you have that capability. Not as relevant for kind of small scale systems, but maybe a smart thing for if a small community can invest in some infrastructure, could get some biogas back off and have a more sustainable energy system for their waste treatment. So it's maybe an option, but it does require a lot of infrastructure. Okay. This one is more of a moving pile system here, where you'll slowly harvest sludge from one pile while accumulating other sludge in a different pile. I think this is a way to mix the piles X number of times per day or per week or whatever. Okay. So that brings us to our kind of point of use systems. How are we going to actually make use of this in a kind of more developing context? Well, the first and probably more obvious thing to do is to separate urine, because if you can do that, there's just a lot more you can do with that. It's going to be, in general, beneficial for your composting. If you have too much nutrients in your compost, I think sometimes it actually becomes a problem where you've got too much ammonia and it's going to poison the microbes. So if you can do that, it tends to be a good thing for both systems, both controlling the amount of water in your compost and controlling any other issues with nutrient balances and stuff like that. Okay, so then you can take the urine, either send it to a drying system to make fertilizer, or directly flow it into some sort of a soak pit. That would be one of those cases where it might make sense to have have a tree near some sort of a pit where you're soaking it into, the tree can benefit from the fertilizer over time, and it's not a big pathogen hazard. Okay, and likewise it gives that moisture content control. So we took a look at this last time, but it really just kind of want to highlight here how that would connect is you can have better control over the biosolids here. You see this person has to come and mix it every so often. If, in addition to collecting it for use, essentially this is saying turning and removal of composted material by hand. So that's going to be not the most fun job in the world, and it's also definitely some pathogen spreading risks there as well. Okay, there's a few other ideas here that we could consider. One would be a solar composting latrine. So essentially you've got a latrine like we just saw. There's some old pictures I found on the web from somewhere. And here we have a system where maybe you can power some of the functions with a solar panel, but what they have here is actually just a solar window. And this is to provide plenty of heat, so essentially a greenhouse effect for the composting material. You're adding that as a way to generate the heat, and it's hard to tell from these pictures, but it looks like those are deciduous trees turning brown in the fall. So it's probably in a northern climate of some sort, or at least not tropical. So I would expect that's a little more important for areas where this would otherwise potentially get pretty cold. Maybe that's not needed, or maybe you don't have to have as big of a solar window design if you're going to already be in a hot and humid area. Might not be as big of a deal, but certainly an interesting design concept to add to it. So here's another schematic and a link there we can take a look at. Just gives a little more description. I think there's a link. I think this link shows kind of both of those, but one of the interesting designs that you could come up with is you have this latrine system and you have a solar window to allow the composting, and then essentially your solids are being collected in a binned bucket system where you have the ability to rotate maybe a few weeks worth of solids are exposed to the sun in the warming window, and then it's a carousel system where once that bin is full, you shift it, and then it gives essentially the solids, new solids entering here. These have been kept there for maybe a week, and then it rotates, and then these have been there for 2 weeks and have experienced the solar, and then in the final one, you're going to empty that as your biosolids for fertilizer or whatever, making room for the next rotation. Of course, you're going to want venting and all of that. So that's kind of an interesting concept, relatively low tech. There again, none of this is going to be a particularly fun job to manage. I wouldn't think. Okay, so just one little final look, kind of the simple case. Could have that VIP toilet latrine system and just simply a solar window there. Of course, you're going to have to consider how to construct all of this to make it structurally sound and all of that. Okay, and actually what I'll go ahead and do is just pull that. So in case you wanted a little bit more context about these projects, this is where I got that information from. It's a neat little article on commercial composting toilets for those. Okay, so any questions on that? Oops. Didn't mean to close that, but okay. Any questions on the composting? Got a biogas video which is related. Again, it's, as I mentioned, it's a little more industrial scale, and it's kind of a funny, the video production quality is amusing, we'll see. But I think it does show some interesting processes and technologies here for you, so I think it's worth worth a watch.
Welcome to a virtual tour through one of BioConstruct's biogas plants. Controlled fermentation of biomass in biogas plants produces a gas that can be used to produce electric or thermal energy on account of its high percentage of methane. The raw materials used in biogas plants, also known as substrates, are often liquid manure, agricultural products and agro-industrial waste. The following animation will demonstrate how electricity and heat are produced from these substrates in biogas plants made by BioConstruct. This biogas plant uses ensilaged maize as one of its renewable raw materials. With the aid of a wheel loader, the maize is tipped into a cement storage bin, which needs filling up approximately once a day. Silo maize is rich in energy and, on account of its high degree of reduction, very well suited for use in biogas plants. This storage bin is equipped with a hydraulic floor discharger that continuously feeds the maize onto a conveyor belt. A scale under the conveyor belt registers the weight of the maize silage. Liquid manure is the most important basic substrate used in this biogas plant. After a short interim storage in the pigsties, it is pumped through pipes directly into the blending pump beside the maize conveyor belt. At the same time, the maize falls off the conveyor belt into this apparatus, which is equipped with 2 mixing rollers. In this way, the maize silage is mixed before fermentation. With this technology, it is possible to supply several fermentation tanks, also known as fermenters, with fresh substrates, even if they are not close together. Liquid waste from the food industry is the third substrate used in this plant. As the availability of such waste varies considerably, a large storage pit should be installed. Integrating this into a hall serves to minimize smells and to help prevent epidemics. Now the liquid waste is heated with hot water to 70 degrees centigrade in a tubular heat exchanger using a countercurrent process. After heating for 1 hour, the hydrogenization of the substrates is complete, so that they can now also be poured into the fermenters. Here is where the biogas is formed. The substrates are continuously stirred in order to prevent layers of material forming at the top or on the bottom. A hot water wall heater heats the substrate to between 35 and 55 degrees centigrade in order to accelerate the formation of methane. On average, the substrate is in the fermenter for a period of around 30 days, before it is filled into another fermenter for a further 30 days to complete the gas formation process. When fermentation is complete, the thin liquid substrate is pumped into 2 reinforced concrete tanks, where it is stored until it can be brought out onto the fields. If the fermenters are filled regularly with biomass, are airtight, heated and regularly stirred, the biogas forms within a matter of days. The formation of gas is a complex and delicate process. The organic fats or carbohydrates contained in the substrates are digested by various kinds of bacteria, and this is the starting point for the development of the gas. If the contents are continually stirred, the gas rises slowly to the top of the container. It consists of approximately 50 to 70% methane, coloured green here, and also carbon dioxide, water vapour, hydrogen and hydrogen sulfide. As water vapour and hydrogen sulfide are problematic for the utilisation of the gas later, it is necessary to treat the biogas now. The gas is first freed from water vapour, coloured blue here. The condensation water is collected in a condensation shaft and pumped out. The aggressive trace gas hydrogen sulfide is now extracted from the biogas in a biological desulfurization plant. By introducing air into the container, certain bacteria cultures are able to establish colonies on the chain. Here they decompose hydrogen sulfide into harmless sulfur and water. The almost unpressurized biogas is then fed into a compressor, where it is brought up to the 70 millibar pressure later required for burning. In order to completely condense any remaining water vapour and to free the biogas from any suspended matter or silicates, the biogas is subjected to a washing and drying process. This is carried out with the vapour at almost freezing point so that the gas is cooled down to a temperature of under 5 degrees centigrade. In order to control the purification of the gas, the biogas is constantly tested with an online measuring system, which records the amounts of methane, hydrogen sulfide, carbon dioxide and oxygen. This guarantees a high degree of efficiency and security. In case of any overproduction of biogas, it is necessary to operate a gas flare, for unburned methane that escapes into the atmosphere is harmful for the climate. The biogas from this biogas plant enables 2-block heating and generating power stations to run and be CO2 neutral. To annually process biogas from 15,000 tonnes of biomass, this plant must produce a total of 500 kilowatts of electricity. Due to the optimal gas processing, the engines can run round the clock for several years with only a minimum of maintenance costs. Up to 30% of the waste heat from the cooling water of the engines is used for the heat exchanger and the fermenter, so that no additional heat is required. The remaining heat can also be used profitably to heat industrial plants, houses or swimming pools. The electric power generated by the generator of the block heating and generating plant is converted to the mains voltage level in the transformer. Then the electricity can be fed into the grid and meets the annual requirements of around 1,000 households.
Okay, so that's pretty much the technological side of things that we really cared about. So last thing we'll do real quick is do a quick Kahoot. Any questions, thoughts on all that? Kind of interesting to think about what all's really involved if you're considering doing kind of methane production, methane, the capture of energy from that. That of course is the large scale system. There may be smart ways to downscale it to smaller facilities, but certainly something good to consider is the scale factor. So when we're back from spring break, we'll have a guest appearance, some stories from working in the third world, and then we'll handle septic systems, probably do some workshop on writing technique and stuff after your next draft is due, which I can't remember exactly, but I think it's early, the first week of April maybe? Yeah, the 4th. Okay. So that'll give you basically a week and a half after spring break is over.
And that's just a page?
Yeah, so for that one, I'm going to grade a page. I'm going to give you critical feedback like I'm doing on your intros right now on the full first page. You can write more than that. I encourage you to, just to get a little bit more of a head start. But I'll give you 1 page worth of detailed feedback, grammatical issues, whatever, I'll be highlighting, and I'll take a look through the rest of it if you do write more, and maybe give you general feedback. But essentially, the plan is to give you 1 page worth of feedback. So I'm asking that you provide me 1 full page of your writing. All right. Well, enjoy the rest of your week and your spring break, and I'll see you guys in a couple weeks.
Thank you.